No, it is not. Thank you. And that chat was probably written like, yeah, 8 minutes ago. All right, thanks for the reminder, Alex. Yes, so this is now it's being recorded. However, I mean, we did cover slides which are, you know, this is just an application you can kind of walk through on your own, I think, and do the numbers. Yeah, so sorry, I forgot to start recording. This one here, I guess the key here is that, you know, depending on how you choose your element to have analysis, right? You can look and you can see that there is there's normal stresses, right? There's also shear stresses, depending on how you're looking at this this element inside, right? The material itself, there's no real element inside the material for a homogeneous material. It's just the same in all directions, which is why you can write these, you can draw these sort of arbitrary shapes, and you can figure out, yeah, by drawing these arbitrary shapes, I can see that there must be both normal stress and shear stress within this material. All right, so composite materials. Like I was saying, composite materials, you're going to run into them, particularly with concrete, right? It's probably one of the most common ones, in fiberglass. But I mean, yeah. Anyway, fiber composite materials. You've got strong fibers, right? And a softer material, maybe, or a weaker material, called the matrix. So here's your matrix, here's your fibers. And now you got to be careful, right? If you have normal stresses and strains, they're going to be dependent on each of these. Well, obviously, as long as the fibers are directional, right, you're going to have stresses and strains that are dependent on the local modulus of elasticity, right? So it's going to be a function of, like, for example, the fiber itself, there's going to be a different stress in the fiber than in the matrix material, right? Because those have different moduli of elasticity. Now, you're still going to have a Poissons ratio, but it's not going to be, again, it's going to be different than a homogeneous object, right? You're still going to write the equations out the same, but they are going to be different in terms of how you apply them to something with a composite, right? Let's see, I think the next one was, I'm trying to remember solution. Yeah, you're gonna have to look in the book for an example on composite materials, because all you have to do is treat the matrix and the fibers separately, depending on what you're doing. But for the normal component is fairly straightforward. And the transverse component is going to depend on Poissons ratio, but you might have to do some fancy math to make it work. All right, this is an example. We're going to work this out on paper here. And what does it tell you? It tells you you've got the circle of diameter, 9 inches, is scribed on an unstressed aluminum plate. And the plate has a thickness of 3/4 inches. Forces acting in the plane of the plate cause normal stresses, and they give you the normal stresses. Sigma x 12 KSI and sigma z is 20 KSI. So notice, right? These are not the same. X and z are different magnitudes, 12 and 20, and then it tells you the modulus of the material and the Poissons ratio. So when you stretch this thing, you want you to figure out, using this information, what are the changes in the length of the diameters. Notice the two diameters, you've got AB and you've got CD. What's the change in the thickness of the plate, and what's the change in the volume of the plate? So let's go through, let's go through that on the document camera. again, one of these problems where I thought it made more sense to walk through it. I can find my pen. Okay. So the first thing we need to write out here is I'm gonna write out a bunch of the equations. First of all, I've got the X stress is 12 KSI. And sigma in the Z direction is 20 KSI. Sigma, let's talk about sigma Y. Now, the stress in the Y direction, we're not actually applying any stress, right? There's no applied stress. So this is going to be equal to 0, this term. So there's no stress being applied in the Y direction plane, no normal stress. Now, I'm going to write out each of these strains as a function of their, well, the applied stress, normal stress, the Poissons ratio, and the modulus, the Young's modulus. This is sigma Y. I'm trying to make sort of a, I'm trying to sort of make a cursive V here for the Poissons ratio, like that. This is sigma Z for Young's modulus. So remember now, I've got, when I write these equations, this is the strain in the X component. Our stress, we're looking at the stress in the X component here. So this is the positive one, right? This is the one that's resulting in a change in direction or change in length of the X component. The stress in the Z is not resulting in a positive stress in the X component, right? We're subtracting off any positive strain. That's where this comes from. But now if this was pushing, then that sign would be reversed and it would be contributing. So just watch your signs of these equations. This is going to be 0, right, which we already said from above. So basically I have 12,000 PSI over 10 to the 6th PSI minus 0 and then minus Poissons ratio is 1/3. 20,000 PSI over 10 to the 6th PSI. Oh, it's, you know what? This is 10 times 10 to the 6th. It's not 1 times 10 to the 6th. 10 times 10 to the 6th. So this winds up with the strain in the X direction is a negative. Oh no, sorry, it's a positive. 5.33 times 10 to the minus 4th. This is inch per inch. Now, the inches are going to cancel out, but the nice thing about doing this is sort of to remind yourself about the units you're working in. Inch per inch, meter per meter. EY, let's look at EY now. EY, there's still going to be some strain, right? Because we've got all these terms. So I'm going to write out, let's see, it's going to be negative Poissons ratio sigma X over E plus sigma Y, or yeah, sigma Y over E minus nu sigma Z over E. I'm using a nu, I guess I should call it V, I don't know. So what do I got? I've got negative 1/3 sigma X Oh, you know what? These are both negative 1/3, and they're both over 10 times 10 to the 6th. I'm just going to pull this out. And here, right, this is 0. If I pull out the negative, I get this plus this, right? Sigma x plus sigma z. So I've got 12,000 plus 20,000 psi. So this is a negative value, negative 1.067 times 10 to the minus third inch per inch. And it's a good idea to sort of check these as you go. Do my signs make sense, right? Well, let's see. In the case of sigma x, it's kind of tough to tell, but in the case, or in the strain in the x direction, because you really need to know. I mean, it depends on the Poissons ratio, right? In this case, and this makes sense, right? It's like the Poissons ratio is telling you that basically 1/3 of this force contributes to elongation or negating the elongation of the x, right? In the case of the y, right, there is no stress in the y, normal stress in the y direction. So we would expect this thing to be squeezed down, to shrink in the y direction. And then we've got EZ. This is an EZ problem, minus mu sigma x. So you can write these whichever way you want. I think your book does the same thing that I'm doing here, just starts off with x, y, z. And so if you're working with the z component, right, these first two terms are going to be negative until you get to the z term. And then this is obviously 0. So here we have, I'm just going to still cheat. 1/10 times 10 to the 6th psi. So I don't have to write this thing twice. Sigma x is 12,000. What do I have? I got a minus and a plus. I'm going to leave that in there. 20,000 psi. The psi's cancel. You wind up with the strain in the z direction is 1.6 times 10 to the minus third inch per inch. Right, so this is using these equations to get the strain in the different directions based on the normal stresses, right, and Poissons ratio. So let me just maybe underlining them would be helpful. Oh, I need some water. Okay, we haven't started the problem yet. Well, we haven't actually started working on anything yet. But you can see how knowing the strains, right, is going to tell us, or it's going to allow us to calculate the lengths, the new lengths of each of these circles, and the new thicknesses, right? So for part A, we're looking at the delta for, I guess, B with respect to A. This is basically the strain in the x. So look at BA, right? BA is the diameter that runs in the x direction. We know the strain in the x direction, right? This is 5.33 times 10 to the minus 4 inches per inch, right? This means that that's the change in length per inch of the material. And the diameter we're looking at is 9 inches, right? So this is just 5.33 times 10 to the minus 4th inch per inch. Now, again, you don't have to write the inch per inch in here, right? This will be the same strain and metric, but it just reminds us, and we're working with inches, 9 inches. So here's where, really, once you use the strain in this problem, you don't have to worry about, I mean, I should have canceled out the inch per inch. So this is 0.0048 inches. And notice, this is a positive, right? So this stretches. Let's see, this is well, we want to know the length of diameter AB. So the actual length would be 9.0048 inches, right? For part B, do I have a second piece of paper? I can fit this on one page. Part B is asking, what's the length of diameter CD? Well, we do the same thing, right? Except now, CD is in the Y or Z direction, right? So we're going to use our Z strain. Oops. Epsilon Z times diameter is, what do we got? We got a 1.6 times 10 to the minus third times the 9 inches. So the length, well, I'll write the number here, 0.0144 inches, and this stretches as well. So the length of CD is going to be 9.0144 inches, right? That gets longer. Part C is asking for the change in thickness, which is basically the Y, right? Y direction is the thickness. And notice the strain is negative here. We've got EY times the thickness. And thickness was given as something, 3/4 inch. So what's our strain? Our strain is negative 1.067 times 10 to the minus third. And our thickness was 0.75 inches. And this equals negative 8 times 10 to the minus fourth inches, right? So plate gets thinner. So we could write like T2 equals, I didn't actually do this. Well, it's, I better just do the simple math so I don't screw up a decimal point. 8 e to the minus 4, because that's what I will do that. 8.9992. 1, 2, 3, yeah. Inches. Oh, not, oh my God. Wrong. The thickness was 0.75. 0.75 minus, I messed it up anyway. Oh my God. Thickness is 0.7492. That would have been easier if I had not. All right, that's the new thickness of the plate. Okay, now the change in, or the volume of the plate is going to basically be the change in volume. We know the original volume. We know the original. Yeah, let's see here. Delta V is basically this little e, right, which is the sum of the Poisson, or the sum of the strains. So let's rewrite this as, well, X plus Y strain plus Z strain. Um, I'm trying to figure out how I'm going to fit this on one page. That's all. You know what? You have the numbers up there, so I'm just going to sum up E for you. E is equal to, let's see, basically 1.067 times 10 to the minus third. What do we got? We got 1.6, 1.0. Yeah, that one is really small. So, so your delta V, right? If you want to know the actual volume, you can calculate the delta V is just going to be 1.067 times 10 to the minus third times, and what do we have for our volume? We've got 15 inches. Remember, this is the total plate, which is 15 inches by 15 inches by 3/4 inch. So 15 inch by 15 inch by 3/4 inch. All right, so delta V is equal to, this turns out to be, well, obviously a plus because I didn't put a negative, 0.180 inches cubed. So what's our normal volume? 15 times 15 times 0.75. So, I mean, this is very small. So V2 or VF equals plus 0.18, 168.93 cubic inches. This over here was 168.75 cubic inches. That's weird. For some reason in my notes, I only calculated the change. Oh, it is supposed to be the change in. Oh my God, I messed this all up. All right, but I mean, you can see, you can just add them to each other. The changes are shown, right? But what's going on here? So we're stretching this thing in two directions, but Poissons ratio is not, it's not a pure conservation of volume, right? Just because you stretch something in one direction does not mean that the other directions are going to fully compensate and keep your total volume the same. Oh, there's something in the chat here. Someone's probably critiquing my, oh, okay. It's like, he doesn't know what he's talking about. He's losing his mind. Yeah. So your change in volume could be positive or negative. It depends on these individual strains. Now, obviously, we see that the strain, the sum of the strains, right, gives you a positive value. But look at these, right? This could easily be, depending on Poissons ratio, right? You might have wound up with, I don't know if you'd wind up with a, yeah, you probably could have. Well, with these, with two stretches, maybe not. With one stretch, you could have wound up with a negative. Let's see, because you would have had a negative here and a negative here. These would have been 0. That would have been 0. This would have been positive. I have to do the math, but it's, you know, you could see, right, if you only had sigma x, these other terms go away, basically, right? And you have positive, negative, negative, and depending on Poissons ratio, right? Actually, you can look at it and figure it out. If Poissons ratio is greater than a third, or greater than a, let's see, half, yeah, greater than a half, you're going to have, you know, shrinkage. Anyway, so that's the way you you do a problem like this. I think the key here is figuring out the strains, using the strain equations and watching your signs, right? Just being alert of what's going on, what's the stress, what's the strain, and then figuring out the deltas that way. All right, so that's Poissons ratio. Let's go back to the slides here. This is all, well, it's all over here, but it's not really, you know, I didn't check their signs. This is what drives me crazy about the book. I've looked in the answer key even, and they mess up their signs. So I've had to correct homework problems before. All right, let's look at Saint Venant's principle. He's French, so I can't pronounce it because I always screw up. I don't know which is silent and which is not. And is Saint Venant? I have no idea. And he came up with this principle that basically, if you transmit a load through a rigid plate, it's going to result in a uniform distribution of stress and strain. And the principle is actually concentrated loads, right, results in large stresses in the vicinity of the application point, right? And it's not until, well, it says it becomes uniform at a relatively short distance from the load application point. So you can see here, let's see, Saint Venant's principle says within about the width, right? You wind up with a fairly even distribution of stress and strains from a concentrated load. If you look any closer than that, you wind up with, particularly down to like, this is a quarter of B, right? You can see there's a significant variation between the max and the min stresses, right? So these are fairly close to 1. They're really hard to see. This is just sigma min and sigma max. This is telling you that, yeah, you get far enough away within about 1 width of this plate, and your stresses, your min and max stress are pretty comparable. As you get closer, right, your max stress becomes a lot more than your min stress. So Saint Venant's principle basically tells you that you can assume that your stress distribution is independent of the mode of load application, right? So it doesn't matter what you have going on up here, as long as you're far enough away from the immediate vicinity of where that application is, right? So it's basically saying these two scenarios are equivalent if you get far enough away from the point application, which would be about 1 width, right? 1 width's length away from the load application. But, you know, in reality, there's very few occasions where you have a lot of point loads. You might have rollers, like some bridges, right, rollers, but even then you have multiple points to distribute, and you have a plate. Usually they're rolling on a plate that's a steel plate on your support material like concrete or whatever. So you never really get a concentrated point load, like you would in theory here, right, on that material. It's spread out over some area. Okay. When you have objects that, well, let's back up a bit. We're leading into sort of stress concentration, and you can have objects that have defects in them, or purposely, you purposely drilled a hole in something so you could, you could use it for something. And this is a source of stress concentration. And now normally when we did some preliminary calculations, we took and we said, okay, the highest stress, normal stress, is going to be on this, like due to these forces P, the highest normal stress is going to be in here, right? And we just calculated the open area and we said it's uniform. In reality, right, the stress actually looks like this. It's very much higher at the center than it is at the outside, where this circle begins, right? Or on the outside of the circle, the outer diameter of the circle. Now, we typically just assume an average stress here. right? The sigma average. However, there's a bunch of different tabulated experimental values for what's called the stress concentration factor, K. And the stress concentration factor is just what's your maximum stress relative to the average stress across this cross section. And you can see this table here, it winds up, it's a nice, it's a fairly dimensionless constant that depends on ratios of things, right? So for example, your stress concentration factor is going to depend on these dimensions. When you look at a table like this, there's typically some key that tells you, okay, this is your radius, and this is half d, whatever d is, right? D. Now this little d is different than the big D, right? So what you're doing to get little d is you're taking diameter minus radius, right? And then dividing it by 2. The little d is basically the stuff in the middle. So once you find this information, 2r over d, and you can read for different values. So you may have different lines on these graphs, depending on what ratios are. They'll plot other ratios as these lines. But this line right here, you can see that depending on your r, 2r over d, your k is going to be either lower or higher, right? And if you look at the limits of this, as your diameter, or sorry, as your big D gets very big, or your radius gets very small, right? You're going to go to a small, let's see, big D, yeah, small number. That concentration factor goes up. As you get bigger in radius, right, your K goes down. So it just means that you're sort of spreading, and this is the ratio of the max divided by the average, right? So think about that, a really tiny hole, that K is much higher at the start of that hole than it is on average, right? Because the average is mostly plate. But as your hole gets bigger, right, the average becomes mostly whole, I guess. But the average is sort of now skewed by the maximum. So it never actually goes to, well, 1 in this case. But you can read these off of tables. Here's a fillet. Let's see, this is probably a good place to stop and start next time. We'll just start here on Wednesday. Don't forget your your test for this chapter 1 here. Remember, it's due by the end of the day Tuesday, so you're not going to get another reminder from me. Let's see. Yeah, test number 1. It opens on, well, it's open now, and it's due by end of the day, February 9th, which is tomorrow. So don't forget to take that. And you have an hour time limit. That includes time to upload your work. Again, if for some reason, I know when you finish the test, right? So if the test, if you started the test at 2 p.m. and it closes at 3 p.m. and you have not uploaded your work, email it to me immediately. And I can just look at the timestamp on the email and the timestamp on the test and say, oh yeah, he sent me the so-and-so sent me the work immediately upon finishing the test. Yeah, so that's what I got. Any questions? Stop recording.